here and 2 after. You have to go on either side, but you don't
You go
count,
3 on one side and
No.
the other.
you don't count all 3 of them. You just count one sigma as plus or minus
6 sigma is about being in the 6th standard deviation on one side.
1. Yeah.
Oh.
So it's not plus or minus 3. You don't get to the
Round
percentage,
like
because 6 sigma says, you know, your 99.99 whatever percent of your product is in the good range.
Okay, it's not 6 sigmas like this, it's
Plus or
6
minus
like
6.
this.
It's plus or
Okay,
minus
Plus
6.
or minus.
Alright, fine, you're right.
What did you write on 11 reports?
I don't know.
No wonder our answers never turned out good. You're doubling our sigma.
Yeah.
Or because,
I didn't take good data.
I was gonna say, or because data's not supposed to turn out good, it's supposed to turn out well.
Ooh, zing! Ooh, zing.
That's why I'm an engineer.
That's why I'm always
Hey,
correcting
come on,
these
come
grammar.
on, we tell people when we're recruiting them about just how good our students are, how well-rounded our students are. Don't give me this, oh, I'm an engineer, I'm just speaking.
The thing is,
I'm just speaking.
I've only
It's gonna be a
taken,
calculator.
I've only taken like 2 gen eds. I still have all my gen eds to take. I
The
haven't
thing
taken-
is, I can attest to Blake's prowess at writing since freshman year.
It's improved so much.
Yeah, he's gotten like 100% better. From
Oh, I
like,
came in freshman year.
from like 6th
Yeah.
grade level to, you're
It
like,
wasn't 6th
you're like,
grade level.
you're like,
To like 11th grade level
yeah,
now.
you're like senior high school level right now.
All right, let's move on. Let's go.
Honors.
Ooh,
Honors.
honors. Senior honors.
Caleb didn't make it back by 302, so we're gonna start with that.
Well,
Shady's not here at all.
Before she made it within her 1 standard deviation.
No,
Alright,
two-
shush.
That's 2 standard deviations.
No, it's
We'll just stand again. Enough already, focus.
No, sorry.
Like those, so you have a clear shot.
Yeah. Beam deflection. So we've talked about all the different sort of
2 plus or minus 1 minute.
stresses.
Nice.
Yeah, I guess so. We talked about all the different stresses that exist in beams. But we actually haven't really talked a whole lot about strain. We did talk a little bit about the deformation. Right? We did talk a little bit about strain in sort of normal strain, right, in an effort to sort of assess as a means of getting at the stress conditions inside the device. We had strain gauges mounted on the outside of the tank, those kind of problems. But with beams, as I mentioned earlier, one of the constraints on a beam may be the fact that it cannot deflect. As we're trying to design a beam, it may be that it's supporting some kind of a rigid structure, like a glass window or a plaster wall, that can't accept much deformation. Okay, there's a limit to how much deformation can deflect. So we need to at least be aware of beam deflections and have a means of predicting the nature of the beam deflection. So if I have a beam like this and I push down with a force P in the center, how's that beam going to deflect?
Can I ask a-
Qualitatively, yes?
Can I ask a quick question? What would be an application where, like a beam would be supporting some load that it could handle a big deflection? I can't really think of any. Besides just like if you're hanging up mass at the end of it or something.
Right, so a flagpole
Okay.
can handle a big beam deflection, right?
Okay.
Or a signpost or something like that, right? Something where the beam doesn't really
Like a
have.
street light or something like that?
Yeah.
Okay.
You can, and in general, the roof of a Walmart
Okay.
can accept a deflection stream, right? Because it's a steel roof, it can accept a bend, okay? So there's plenty of cases where it can, but you're right, there are a lot of cases where it can. I mean, if it's a beam supporting a concrete platform or something, concrete typically doesn't want, you don't want the concrete to flex. Okay, so what's this going to look like? If I push down with a force P there, how's it going to deflect? Okay, so is this point going to move?
No.
Okay, what about over here? Is it going to move?
Yes.
Where?
Down.
Down. Okay, is it going to move here?
Yes. Yes, it is gonna move to the right, no left.
Okay, we're only talking about the vertical deflection.
Okay.
What about this?
Yeah, that's up.
Right, so you can kind of qualitatively tell that the beam deflection is going to go like that. Right? That red line is called the elastic curve. So we know qualitatively, in almost all cases, I mean, most of the time, you have a load distribution on a beam, you can qualitatively tell generally how the beam's going to deflect. So when you draw the elastic curve, you're drawing it, actually I guess I should have drawn this through the neutral axis, but anyway, you're exaggerating. We don't expect it to actually bend that far. Right? But it's exaggerated enough that we can plot it out. And from here on out, we know it's going to be a straight line. Right? This end is just going to bend because there's no other forces on it. So there's no internal shear or moment in that piece at the end. So we can draw the elastic curve qualitatively, but generally speaking, we don't want a qualitative measure of deflection. Right? We've got, okay, never mind the fact that that's not the right spot. We have this beam deflection we're going to call V. And we want to quantify we need to quantify V. We need to quantify that beam deflection. And probably V as a function of that, because we want to quantify it along the beam at all the points. All right, in other words, we want to have a quantitative elastic curve, not just a qualitative. Okay. I forgot to fire off the thing here. Oh, that's it. No, wrong chapter. This is chapter 12. Hi
You're
there.
just making noises. Yeah, we have nothing. We'll start. What you do it? Oh,
Okay.
computer engineering project. Dude, not off the weed whacker.
So what we need to get at is we need to get at the internal moment. Right? Because the internal moment is the thing that's bending the beam. Right? So we have this beam, and you could probably qualitatively determine that it's going to go down and then down again. Right? So you can qualitatively look at that beam that's up there. The loads applied here and here. And draw an elastic curve. You know it's fixed here. It's fixed there, so you know it's going to do some wiggle like that. So what we want to do is we want to find out the moment at each point, and we have to first find the internal moment. So for this graph, we have a shear diagram. You know, we do a free body diagram. You know, we do a free body diagram of the whole thing. Find out what a shear diagram looks like. Right? Take the shear diagram, integrate it to give us a moment diagram. And then, from the moment diagram, we can know at least qualitatively where the inflection point is, right? Everything left of C has a negative moment. Therefore, will be concave down. Everything to the right of C has a positive moment, and therefore will be concave up. And so we've made at least a bit of progress by identifying the inflection point in between the two. Does that make sense? Okay. Next step now is.
Can you go back to the shear one for a second?
Okay.
Okay. And then, I'm good now.
You good?
Yeah.
Okay. And then, okay, so what we're going to do is we're going to take the same approach as we have with everything else. All right, we want to find out the behavior of the beam. We take a slice, we find out the slice and the behavior of that slice, and then we integrate that across the beam. Right? Take the same approach we did with bending moments, with torsion, and everything else. We've done a slice and then integrate it. Because you remember this process we've done? Okay. Okay, so here's our beam. It's a different one than the one that was on the first page. We've got some load out there on the left. We've got a load over on the right, an applied moment, okay? And we're going to take this slice dx. in the center. And we're gonna look at what's going on at that dx as a result of the supplied moment. Because the moment is what's causing it to bend. Okay? So let's back that off in the corner, and then we'll take out that slice. So we have a slice of our beam. I don't know what beam it is, it doesn't matter. We got a slice of beam, neutral axis through here, has a dimension dx, and then there's a particular plane of interest up here, and that one has a length of ds. Right, and we're some height y above the neutral axis. That make sense, everybody? You understand how I'm defining my positions. As I bend that up, the right side of my box is going to become inclined with respect to the left side of the box. Right? So this thing's going to become like a pie wedge. So I bend it up. Okay? And obviously exaggerated in this picture, but that pie is going to have some center. That's what O prime is there. That's the center of curvature of that pie wedge.
But that's not actually on the beam, that's just a point in space.
That's a point in space.
Right.
So there is a distance, rho, that represents the radius of curvature of the neutral axis of my slice. Yes.
So, the more you bend it, the more that it extends upward towards O prime.
No, the more you bend it, the more O prime comes down toward the beam.
Oh,
Right? O prime in this case is at infinity.
okay.
Here, O prime is down. If I bend it more, O prime will come down because this thing will slant out more.
And if you bend it at a radius 0, O prime's right at the edge of the beam.
Well, I can't get to radius 0. I mean,
Yes.
yeah, you take a coat hanger and bend it back on itself. Eventually, yeah, but
Okay.
we're never going to get to that point, right? We don't want lots of deformation. Okay. We're just talking about deformation. These are all, we're assuming we're staying in the elastic behavior. We're sticking with elastic behavior for everything. So everybody okay with the radius of curvature is that distance out there, right? And then here's my new ds. ds and dx have become arcs in this picture, right? So this dx here is the same length as the dx over here, because that's the neutral axis. It has not experienced any normal stress.
But like the length of like the curvature, right? Not just
The
a
length,
straight
right, the
line.
length of the curvature part
Okay.
is
So it's-
the same as dx. We're eventually going to, right, I mean, we're going to eventually let dx go to 0, so that
yeah.
those two will be the same, right? As dx goes to 0, that's, there is no curvature, right? It goes smaller.
Yeah.
This right here now is ds prime, that's our new ds, and it should be less than the original ds, right, because it's compressed on the top. Right? Okay. And we still have the same y dimension here. Okay. And the reason that this happened is because there is an internal moment M within that section. Yeah. And there's an internal moment that's caused it, yeah?
Sorry, since dx is the neutral axis, it wouldn't have an arc, would it?
That's what she just asked.
Oh, did she?
So in the limit, as dx goes to 0, no, it won't.
Okay.
But I've drawn it here as a big, oversized chunk just to sort of get so we can get the relationships between everything.
So it still would even at large?
So,
Yes, yeah, I would have to. Yeah.
but so it
But the
bends,
distance doesn't-
but it doesn't stretch.
Okay, gotcha.
Okay, the distance along that arc is still the same. Okay, and then we're gonna have one more term, and that's theta, the angle, or d theta rather, the angle associated with this incremental piece. Okay? Does that make sense to everybody? The drawing? Same as the drawing over there on the slide. Okay, so let's, go ahead.
So what is the purpose of finding the row?
Yep, I'm just about to show you.
Okay,
Okay.
I'll do this one.
Okay, we can express dx in this second case here is rho d theta. Right? Similarly, we can express ds prime as rho minus y d theta. Right, slightly smaller radius to the ds prime location. And we know the original ds is equal to dx because it was undeformed. Right? Ultimately, what we're trying to do is find rho, right? Trying to find out how much it's bent. Right? We want to get something in terms of rho. So, the strain at point S, all right, I'm sorry, strain at point Y is equal to ds prime minus ds divided by ds. Right? The change in the length divided by the original length. That is the strain at point Y. Ds prime is rho minus y d theta. Ds is the same as dx, so it's just rho d theta divided by rho d theta. The rho d theta terms on the in the numerator cancel out, and I'm left with minus y d theta, oops, d theta minus y d theta over rho d theta. D thetas cancel out, and we're left with the fact that the strain is equal to minus y over rho.
I don't know. Just trying to
Are you taking dynamics next semester? Are you taking dynamics? Come in here and take that middle seat. First thing.
I don't know if I really want to get in the middle of that. Plus, if I sit there, they'll just move over here.
I'm just trying to be a good student.
Yeah, but then if they move over here, they'll just don't be here. All right, so I can rewrite that then as 1 over rho is equal to minus the strain over y. Okay? But,
Why don't you just say row equals?
for a reason. Always been. Okay, but we can express strain, right? We can, good Lord. You can tell it's the end of the semester. We want to get this in terms of moment, right? The whole point is to figure out how the moment is creating this. So how am I going to get this in terms of moment? Well, the moment is, it's a force, essentially. So I want to get my strain expressed in terms of the loading component, right? So I want to take my strain and recognize that that is sigma over E, right, for as long as we're in the linear regime. And sigma, what's sigma? Colin, what's sigma? How can I express sigma? What's causing sigma? What's causing this whole thing?
Our shear force on.
No, it's not the shear force. The moment. How do I get sigma?
Is that why I brought?
Yeah, but your name's not Colin. My over I E. Right? plug that back in here, 1 over rho is therefore equal to minus m over IE. And actually, the minus sign disappears, should have put it up here, because this is compressive. Right? A positive moment yields a compressive stress. So that's why it's stress, they have a minus in there. So 1 over rho equals m over IE. So we can find the radius of curvature at any point if we know the moment and the moment of inertia of the beam at that point. And E's a constant for the material. But that still doesn't get us to what I really wanted, which was V. And I really want to know, what's this deflection look like? So I'm going to we're going to pull in some calculus. 1 over rho from calculus, where V is sort of the, so I'm using both Y and V to represent vertical dimensions here. Y is the dimension within the beam. V is the deflection of the beam. Okay? So Y is a position variable. V is a measurement, a measured variable. Measured
V is
function.
just like how far the neutral axis was,
Right.
or the whole beam, I guess.
Right. Yeah, but the neutral axis is where we track it.
Yeah.
So V is the movement of the neutral axis, whereas Y is a position variable from the neutral axis. Okay? Does everybody understand the distinction? I mean, they're both in the vertical direction, but they represent different things.
Wait, going back a step, I think you explained it, but why is there no negative U down?
Because the stress in the beam, I'm applying a positive moment, right? It's one that causes a concave up surface. That positive moment creates a negative stress.
Yeah.
The sign of the moment and the stress are opposite one another. So I have to plug in a negative value for my stress. Then I have a minus sign up here, those two minus signs cancel each other out, and I'm going with that.
Gotcha.
Okay? Okay, we're good? Okay. So from calculus, we have that. The inverse of the radius of curvature is the second derivative of the deflection divided by 1 plus the first derivative of the deflection, or the slope, squared to the 3x. And dv dx is the slope. Right, v is the deflection. And dv squared, the second derivative then is the curvature. Okay, so that just comes from calculus. We're just taking that for granted. You can go back and do the derivation if you want to.
So V is the actual distance.
V is the displacement at that point.
So
Vertical displacement of the beam.
what is this?
The deflection.
Slope of the physical distance?
So dv dx is the slope of this red line
Oh, of the, okay.
at this point.
So V is.
V is the
this
deflection.
line, the slope of this.
The slope of that line is dv dx, and the curvature of that line is d squared
Okay,
v
that
dx
makes
squared.
sense.
Okay? So the three characteristics of this thing are all lumped together. So V is the function. Yeah, actually V is not in there, but anyway, V is the thing we're trying to solve. Okay, so that's ugly, right? Equate that over here. Ugh. Right. But we're going to make one small approximation. That is, we're going to acknowledge the reality that this thing is going to yield before it bends too much. And if you can go through and do the calculations and find out, for even small amounts of V, you're getting very small amounts of V before this thing yields. In other words, if I'm going to get this top bit here to a yield point, my radius is still going to be huge. Right? So we're going to make the assumption that the slope is small, so a small number squared
It's really small.
is really small or negligible. So we're gonna say that that's approximately equal to d squared v dx squared.
Oh,
What's that?
you said it's approximately equal to, and I was looking for a number two.
Oh, I got you. Okay, so we're essentially saying it's gonna be small slope.
Yeah.
And if you go back and run the numbers, you find that indeed that's a very small slope. So, what that says then is that m over IE is equal to the second derivative of the deflection.
So
Or-
we're saying that one over the radius is equal to the curvature?
1 over the radius is equal to the curvature in the small deflection approximation, yes.
Okay.
Or the small slope approximation. Okay, so if I rearrange that and say m then is equal to e I d squared v dx squared. Second derivative. Right? But m varies as a function of x. Right? M is different at each point along the line. And v of x is the derivative of m. Right? M is the interval v. Remember? That's how we got the shear and moment diagram. So v of x then is ei times the third derivative of v. And if you remember, the loading distribution for distributed loads is dv dx, because v, the shear, is the integral of the load. Right, for a distributed load, we integrated the load to get the v. So w of x is equal to ei times the fourth derivative of v.
Right, and so.
Sorry, what?
V-
Sorry, Eric.
Sorry, V is shear, but then the V on the right side is the one we're talking about, the displacement.
The v on the right side.
So like,
Oh, yeah, this is, yeah, you're right. This is big V, and this is little v.
yeah,
Okay, so those are different.
Yeah, yeah. This is the shear V, that's the displacement.
And then, sorry, what?
Lowercase v.
Yeah, I just missed what you say W of X was?
The loading distribution, remember, if you
Oh,
had a
okay.
distributed load, the W of X was the, okay? So we have the slope of the surface is dV dx. The deflection of the surface is just V. So V, its first derivative is the slope. Its second derivative, within a constant, is the moment. Its third derivative is the shear, and its fourth derivative is the load distribution, the distributed load. Right? So if I want to get back and find out what the deflection of the beam is, I have to take one of these and integrate it,
However many times.
however many times it
With
takes.
respect to X.
With respect to x, right? So if I know m of x, then I can integrate m of x dx, and that's going to give me, I don't know if there's a letter for slope. I don't know if they have a particular letter for slope. I don't know if they do.
little one,
What's that?
little one.
Well, that's fine, yeah. I don't want to confuse matters too much. I don't know that they do.
Just make it X.
Draw a little right triangle.
Yeah, I'm just seeing if they've got a slope. Hold on. Yeah. Nope, nothing. Okay. Little slope. And interval of the slope dx is equal to deflection. So I have to integrate twice to get the deflection from the moment. I'd have to integrate 4 times to get it from the local distribution directly. Each time I do an integration, I'm going to pick up an integration constant. Right? So its slope, well, the slope is going to include some f of x plus c1. And the deflection then is going to become v of x plus c1x plus c2.
Sorry, maybe this is a dumb question. So we wouldn't be able to use the length of our beam as limits, is that?
Yeah, we will.
Okay, sorry.
Okay. So the functional behavior is, this is the functional behavior. Then those constants are going to be determined by the constraints of the system. Right? We know, for instance, we know, for instance, that if our surface is pinned, so depending on which one we get anywhere from 2 to 4 constants that we've got to figure out, right, depending on what we end up starting with. So we have 2 to 4 integration constants that have to be solved. So to solve them, we're going to use our boundary conditions. Okay, use the constraints on the beam. So for instance, anytime I've got a pin, right, so like there on the left end, I have a pin. We know that the deflection at the pin is 0. And we know that the internal moment at the pin is 0. Because the pin can't support moment. Or a roller. That could be a roller too. So both of those two ends, we know that the displacement is 0, which you guys have already talked about, right, as we did the qualitative one. And the moment is 0, we just know they can't support it. If it's a pin or a roller in the center, right, so a pin in the center could have a moment. Right, when I did this one up here, there could be a moment right there. Right, a pin or a roller at the end does not have a moment. But a pin or roller in the center can't have a moment. You see that? The example on the board here. Therefore, we only have that the deflection is 0. If the pin or roller is in the center. If we have a fixed support, so beams concreted into a wall, then we know the deflection is 0. And we know the slope. Theta. I knew it was. Couldn't remember what the symbol was. Theta, the angle. And so in this case, theta at some point, the deviation of how much has changed from the horizontal. So at a fixed support, we know the displacement and the slope is 0. At a free end, so the left-hand end of this thing, we know that the shear is a capital V now, equals 0, and the moment equals 0. Right? The shear moment always returns to 0 at the end, at a free end. And then finally, if I have an internal pin, That is, if I have two beams pinned together, we've done a couple of those problems. So we have an internal pin, all we know there is that the moment equals 0. So those constraints, when applied to our solution, will hopefully allow us to find the additional constants. Okay. Notice most constraints B equals 0. The deflection equals 0. At most of the constraints, the deflection equals 0. Okay, so we end up with this thing, the deflection. If we start from the moment distribution, the deflection has two constants. But I know that it's got to equal 0 in the pin at the end. So it helps me set C2 at least. Okay. Does that make sense?
The only one I'm confused about is the pin or roller in the center.
Right, so this is a pin or roller in the center. The moment is not necessarily 0 right above that. Right, the deflection is 0,
Mm-hmm.
but this thing is bent.
Mm-hmm.
Right, it has some net concavity. It has a negative internal moment.
I got you. Okay.
Okay.
But that itself kind of supported a
You can't, no, right, the roller doesn't support a moment, but the moment could exist at that location in the internal moment, right? Yeah, these are all the internal quantities now. These are all beam quantities. These are not, none of these involve applied forces or loads. Yeah.
What we talked about, not yesterday, but Wednesday, that you couldn't have two pins in a beam.
Right, well, yeah, you don't design it with two pins, you over-constrain the system.
So if there was a pin there, there would have to be a roller at the other end.
Right.
Okay.
If it's gonna be, I mean, if you're gonna, this is something we should have covered back in statics. Right, you can't over-constrain the system, you can't under-constrain the system. You can only solve for a ideally constrained system. So if you put two rollers, it can't support horizontal load, so you can't solve the problem. Right?
Right.
If you put two pins, now it can support, or you can't distinguish the horizontal load at either end. And so, well, I mean, you can still solve it, but there would be an internal normal stress created by virtue of the fact that there are the two pins. A thermal stress at the least. Right? So it can do it, but you're adding an additional stress that you don't need to. Right? I mean, the reality is, beams, actual beams on a building are pinned at both ends. Right? They bolt this beam onto this girder and bolt this beam onto this girder, and
Okay.
you know, it's constrained at both ends. So there's a normal stress that's created in that process. But by doing this, we can't have, there's no normal stress in this beam. The
We don't
beam
build
is-
buildings like that, right?
No, that's what I'm saying. They build bridges like this. They do build bridges like this. Right? Because the bridge is going to expand and contract.
Right.
And so they create expansion joints, and the bridge is able to slide. I mean, it's not necessarily a roller per se, but
That's
it's
what
able
those
to
like
slide.
little rubber things are on the beginning and end of bridges.
Rubber thing.
Like there's like this much of
Just the distance.
Or their teeth,
Oh, okay.
you know, that slide together and apart. But that's what you get on the bridge, on the superstructure. Underneath, there's some kind of a roller type support. Okay. Because again, the bridge is going to swell and compress. Whereas in a steel superstructure, they build in the fact that there's going to be potential, that thermal stress is going to create normal compression or tension in the member.
But they can't be good for building buildings.
Well,
right?
generally speaking, buildings aren't as long as bridges, right?
Yeah.
So the bridge, that can accumulate quite a bit, right? You can get some real big deflections in the bridge. So buildings, but it's still designed around in buildings. I mean, you still have to worry about coefficient of thermal expansion, mismatches, and that kind of thing.
So that's why super tall buildings are impressive feats of engineering.
Yeah, well, among many.
Among other things.
Yeah, the Burj Khalifa, the most impressive thing to me is the fact that they were able to pump concrete up to the top of that thing. You know about the Burj Khalifa, tallest building in the world? It's almost a kilometer high.
Oh, okay. In Dubai?
In Dubai, yeah.
They pumped what was inside?
Concrete, how'd they get the concrete up to the top? Because the, concrete.
Gotta be quite
the floors are
long.
concrete.
Wow.
That's actually set many world records building that building. That was one of
Is that,
the highest concrete pump.
is it on where
Wow.
the island those things that they use?
Dude.
Island things.
It smells so special.
No, Dubai is a sand. I mean, Dubai is sand. So they have,
That's
in order to build these tall buildings, they build, you know, the oil money just being spent wild and crazy. They have to pour down a long ways to get foundation.
But didn't Saudi Arabia decide, like, you know how like they have man-made islands that look like things?
Yeah.
Don't they have plans to make a new really tall building?
Saudi
Could be, could be. No,
This isn't in Saudi Arabia.
No, she's talking, she said Saudi Arabia, but
Yeah.
it's Dubai and UAE. But yes, I don't know specifically about the really tall building, a particular plan, but now that the Burj Khalifa is up, I'm sure there are plans to try to build one that's bigger. But Burj Khalifa is enormous by comparison to even, number 2. You know,
Really?
It is incredible. Okay, but the point is, there's a lot of impressive things about big, tall buildings like that.
Right.
Okay. All right, I've actually got one more thing. I'm just gonna go ahead and cover superposition real quick. So we're not gonna get to any problems today, but then essentially the next 3 lectures are gonna do just nothing but problems. Okay. So we can work on this, but it all kind of fits together and I didn't want to lose momentum. Okay, so we've got this process now for figuring out what the deflection of the beam is, based on the internal moments and everything. And it will be presumably in terms of these constants, so that we have an opportunity to design around that. Right? We can do it in terms of the constants, right? E and I in here, we can leave as E and I all the way through the process. And if we want to minimize our deflection, we know what we're going to have to do to I to get the deflection. Okay. Oh yeah, superposition. Okay. So it's also possible when you have a very complex loading structure like we have up here to use superposition because again, all of these loads are going to give rise to linear relationships, right? Even when we get down to the, where are we? Right here, right? Even this expression, W of x is equal to E I e to the 4th v over dx to the 4th. Says that there is a linear relationship between v and w. In that, if I double w, it's just a constant of 2 that's going to be carried through my integration. Right? That factor of 2 is going to carry through. So this is a linear differential equation. It's still a linear relationship. So since it's linear, we can use superposition, just like we did for other things that we've done. Right? So one of the things, if we've got a complex loading like what's up there, you can find the deflection, v of x, for multiple different loads, and then just add the v's at the end.
What do you mean for multiple different things?
Well, right there, we've got 3 loads applied. We've got W, P, and M. So I can find V due to W, V due to P, and V due to M. Add them all up and get my total V of x. Right? You can see it in the integration too. If I integrate each piece, if I have M plus whatever plus, you see what I'm saying? We have pieces that's all going to be added. So, in sort of summary, V of x then is equal to the sum over I, the i's of x. And the same is true for theta. The slope, or the shear or the moment. We've already done those. We've already done the superposition of the loads. Right, so we can do the superposition of the position, superposition of the deflection and the slope. So if you look in your book, in Appendix C,
Yeah.
Do you have appendices in your book? Make it hard for you. Nope, no appendix. So those of you who have a legal copy of the book, if you look in Appendix C, there's a whole table of slopes and deflections of simple beams. So here, I'll allow you to see this. But I'll show it to them.
Yeah,
So all these simple beams, right? So you've got the slope and deflection formulas for each, for each sort of basic structure of beam. So that wouldn't work with this, because this is not a simple beam, it's a cantilevered beam. But simple beams are those like this, that are supported at both ends, or a beam that is cantilevered. So the table includes simple beams or cantilevers, where they're just cantilevered out from a fixed support.
Where it is just cantilevered out.
Or it is just cantilevered from a fixed support. Those are the two that are tabulated. And those tables are also going to be on the FE exam, in the reference manual for the FE exam. Okay. So everything you get in the appendices here, you'll have for the FE exam. Yeah.
Will that be a thing for the like tables and everything you get? It sounds like it's gonna be a booklet.
It is a book. It is a book. It's about that big.
so you really.
Actually, it's not true. You guys are going to take it electronically now. The FE is now online, so it'll actually be an electronic, a PDF file.
Do we take this at the end of
If you choose to. If you choose not to,
Yeah.
then we give you an exam. And that's our E-ish type exam.
Oh, I see what you're saying.
Is Blake allowed to use his abacus on the exam?
Abacus.
We'll see what we have.
You don't like it, you know.
Okay. So anyway, so the point is you can use the tables to quickly get through any kind of simple beam configuration. You don't actually have to do all the integrations. Okay, they're covering the basic integrations just like they did for moments of inertia. Right? You know how to do integral of x squared dA, but it's a lot easier when you say, oh, it's a triangle, I can tabulate, that's tabulated, let me look it up. Okay. So you have to understand this, and in fact, if I'm not mistaken, we'll do that for one or two beams, because these are not simple configurations, these are not simple beams. But that top one is, the bottom one is, right, those are, the bottom is supported at both ends, the top one is cantilevered. Okay. So, but when they're not, you have to actually you have to come up with a V distribution or an M distribution and then integrate backwards. Okay? And again, use your oh, I forgot to talk about this too. Shoot, I'm almost out of time. As you're doing each section of the thing, so if I were looking at this beam, this section would have one particular V of x function, right? The next section here would have a different V of x function. And this third section would have another V of x function. So I have A, B, and C. I've got three different V of x functions in those three regions. So when I solve this, I can define each function independently with its own x. Right? If I want to define this as xc, right? So x is 0 here and it goes this way when I'm doing c, but it's more convenient for me to define xb this way. That's fine, I can. Okay? Or maybe for this one, it's more convenient to define xa back to some initial reference. You can define it however you want, okay, within the functionality of that thing. Because you're going to be able to use these constants to adjust at the end. So all you have to do is you have to know that at this point, whatever the final value for xc is, has to be the initial value for xb in terms of deflection and slope. Right? The beam does not undergo any kind of change, any kind of discontinuity. There's no discontinuity in deflection or slope on the beam. Right? Beam doesn't go down and all of a sudden turn back up, you know. It has a continuous flow. So since we know these are continuous, I can find V sub C at this point, and V sub B at that point, and have to know that those two have to be, yeah.
What about some sort of a sine function? Why can't we do that?
What do you mean, why can't you do that?
Well, it just seems like the way you have it written right here, it looks like it could be like a sine function continuous from A to C,
It could be,
but not necessarily.
but not necessarily.
Okay,
I mean, it's possible,
right.
but you'd have to have just the right load, right? So ultimately, what that means is if V is a sine function, then W is going to be a sine function. Right?
Right.
Because the fourth derivative of a sine is a sine. So if indeed I had a sinusoidally distributed W on top of this beam, right, and it was cantilevered so there was nothing else acting on it, then I might have a sinusoidal deflection. Or it might not.
Yeah,
Because,
so,
because we can still have the integration constants so that, you know, in this case, you've got an extra force sticking up here, so just because W of X is sinusoidal at the top, doesn't mean it's not the only load. So you'd have to do superposition. You have a sinusoidal thing from W of X, but then you'd have some other deflection due to this force pushing up here.
so, is our region C, do we average the V function across C?
No,
Is it like an average, or is it?
No, you plot deflection as a function of position, right? I mean, this red line has some functional behavior. Okay. So we're deriving here, yeah, that's supposed to be a lowercase v. We're deriving v as a function of x, an actual expression of the line.
So, like what you said with the superposition though, and then comparing it to that, do you cut it off at each place there's like a new loading?
So you functionally, right, so if you did the shear and moment diagram for that, I mean, I know we're over time, so if you gotta go, you gotta go. But if I do the shear and moment diagram for this thing, right, I've got a downward force acting out here, right? So I'm gonna have, oops. I'm gonna start off with a negative shear. And it's gonna go over to here. And I have an upward force, and that upward force is probably bigger than the negative shear. So it's gonna go up to here, right? As I come across, then I have a downward force here, that drops my shear, and then, no, did I do that right? Oh yeah, this one I think is pushing up. I think if you do the analysis, put equal loads here, I think that one's pushing up. So anyway, so that's what your V looks like, right? So your moment diagram, can't remember, is going to do, it's going to do this, and then this, and then, no. I don't know. I don't have real values here. Something like that, maybe. I don't know. Yeah, I'd have to have real numbers to know. Okay, so that's my thing. So what I'm going to be concerned about then, sorry, this is supposed to be there, is the functional behavior in each region. Because this function is different than this function, which is different than this function, right? So the breakpoints are defined by wherever my shear and moment diagrams undergo changes.
So then how do you have more than one? Like more than one in each place though?
So, I don't know what you mean by more than one.
Like with the superposition,
Superposition only applies back to the displacement and slope, the deflection and slope. So I would integrate this twice, and I would get a deflection map across there, and a slope map. And if I just integrated this, it wouldn't necessarily be a nice continuous function, so I'd have to use my integration constants to get these continuity at these 2 points. but I would have some kind of map
Mhm.
of V and theta. And then, but if I did it separately, if I just did, okay, forget it, I'm just gonna do each force individually, I would get one V map, I would get a different V map, and I would get a third V map.
Oh.
And I would add those three together, and it would give me the total V
Now
map.
I see what you're saying.
Okay?
Yeah, that makes sense now.
Okay. You guys good? Good. It's amazing how much more we get done
No practice.
when, no practice, yeah. 7 extra minutes? No problem, I got it.
Well,
I got too much
I'd rather
time.
do 7 extra minutes and talk about cool stuff for 5 minutes.